Hello everybody, so this is the second video associated with Chapter 2 of the Introduction to Quantitative Finance class. So in the first part of the chapter, we've introduced a one period two-state binomial model where the stock price could go either up or down. And then in this very simple model, we showed how to price option an option based on the construction of a replicating portfolio. So we've identified a portfolio whose terminal value was equal to the payoff of the derivative under all scenarios. And then through the law of one price, we concluded that the price of the derivative had to be the same than the initial value of the portfolio. And then we went on calculating this value. So we're going to generalize all this theory now to another model, which is a slightly more complex version of the binomial model. So this is the model we're going to present now is a generalization to the binomial model to multiple periods. So the first version of the model presented earlier in the earlier video had a single period, whereas now it's going to have multiple periods. So let's consider the multi-period case. There exists many time steps in that model. So the time goes from 0 to 1 to 2, 3, 4 until capital T. So there's a total of capital T periods in the model. And then once again, we're going to assume that we have two assets traded on the market. The first one is deterministic and grows at the risk-free rate. So BT is assumed to be equal to exponential of RT. So this is an exponential growth at the risk-free rate R. So R, which is assumed to be greater than 0, is the continuously compounded risk-free rate for each period in the model. So then for the second asset, which is the risky asset, we're going to postulate the following dynamics. So here for consider M, so MJ, J goes from 1 to capital T, are assumed to be IID, so independent and identically distributed Bernoulli P random variable. So what's a Bernoulli P random variable? Recall here, a random variable x has the Bernoulli P distribution if it's worth either 1 with probability P or 0 otherwise, which is with probability 1 minus P. Okay, so we're going to assume that all these MJs are Bernoulli with probability P and that they're all independent. Furthermore, again, we're going to consider two constants, U and D, where U is strictly greater than D. And we are going to postulate the following dynamics for the price of the risky asset. We're going to say that the time t plus 1 value of the risky asset is its time t value, so its value at the previous time step, times u to the power mt plus 1 times d to the power 1 minus mt plus 1. Okay, so this looks complicated, but recall that mt plus 1 has either 1 or 0 as possible values. So if mt plus 1 is equal to 1, this guy becomes u, this guy becomes, so 1 minus 1 becomes 0, d to the power 0 becomes 1. So this is simply STU. Conversely, if mt plus 1 is equal to 0, this guy here becomes 1, this guy here becomes d, so that whole thing becomes STT. So this means that the stock price or the risky asset price at time t plus 1 is either STU if mt plus 1 is equal to 1 or STD if mt plus 1 is equal to 0. Okay, so you can think of the MJs as random trials, kind of playing head or tail. And if the trial is equal to 1, if it has a success, then the stock price goes up. If it's a failure, then the stock price goes down. And this trial is repeated at every period. Okay, so we can represent the dynamics of the risky asset through this following multi-period tree. So the initial value of the risky asset is S0, and then at time 1, either it goes up with probability p or it goes down with probability 1 minus p. Then at the next step, at time 2, you can take the time 1 value, either it goes up from S0u to S0u squared, or it goes down to S0 ud here. Conversely, if it had a downward movement in the first period, it can go either up to S0 ud or down to S0 d2. And one thing that is important to notice is that this tree is said to be recombining. So if you have an upward movement followed by a downward movement, or a downward movement followed by an upward movement, you end up at the same value here, which is S0 ud. Okay, so the order of the movements doesn't matter to determine where you're in the tree. The only thing that matters is the number of downward and upward movements. So for example, if you go up, up, down, or up, down, up, or down, up, up, you always end up at the same value, which is S0 U2D. Okay, so this is why we say the tree is recombining, because the various paths, they recombine at the same value. So for two paths, if you have the same total number of upward movements, you're going to end up at the same value for the risky asset, even if the order of the movements are different. Okay, so it's quite straightforward to show. We won't give the formal proof here, but you can show that ST, the time t price of the risky asset, can be written as its initial price times u to the power m, capital MT, times d to the power t minus mt, where mt, it's the sum of the indicators mj, where j goes from 1 to t. So how can we interpret capital MT? Capital MT is the number of upward movements of the stock until time t. So the stock price at time t is its initial value times u to the power, being the number of upward movements, times d to the power t minus mt. So t minus mt is the number of downward movements of the stock. Furthermore, because all these MJs were Bernoulli P and independent, then the sum of these Bernoulli P's is binomial, has the binomial distribution. So MT has a binomial distribution with parameters T. So T trials, each trial has a P probability of success, so it's binomial TP. Okay, so this is the dynamics of the risky asset under the generalized model. So we can see that it extends the one period model by adding some more periods. Now we're gonna do a bit of terminology. So we'll define some things which is required to understand portfolios in this multi-period framework. Okay, so our first definition is the following. A stochastic process is a sequence of random variable indexed by time. Okay, so x0, x1, x2, x3, x4 until x capital T. This is a stochastic process because it's not a single variable, it's a sequence of random variable, and each of the random variables in the sequence is associated with a time step. A quick note here, we could have that each of the x's could be a vector. So sometimes we have random variables in one dimension. Sometimes we could have multivariate random variables where each of these x's, so x0, x1, x2, etc., could each be vectors of random variables. So multivariate random variables. Okay. Now, this allows us to define what we call a trading strategy in the multi-period framework. So a trading strategy here that we denote by theta, it's a sequence of theta t's, so theta 1, theta 2, theta 3 until theta capital T, where each of these theta t is composed of theta ts and theta tb. Okay, so here the intuition where I'm just gonna give the intuition. Theta TS will be the number of shares of stock in the portfolio from time t minus 1 to t, and theta TB will then be the number of shares of the risk-free asset in the portfolio from time t minus 1 to t. Okay, so here, this is a stochastic process because it's a sequence of random vectors uh, where each element of the sequence corresponds to a sometime. Okay, so a trading strategy represents the composition of a portfolio at each time step. Okay, so theta 1 represents its composition from time 0 to 1, theta 2 represents its composition from time 1 to 2, etc. until time capital T. Okay, so a trading strategy is a stochastic process, which we showed here, which is predictable. Okay, so here we won't give a formal definition of predictability here, but for the purposes of this course, predictable means that theta t is exclusively a function of variable s0 to st minus 1, meaning that they don't depend on st plus 1, st plus 2, etc. Okay, so the intuition about that is that theta t only depends on information available at time t minus 1, and it cannot depend on future information. Furthermore, here the trading strategy starts at time 1, but for convention, to ease notation, we can define theta 0 being equal to theta 1. Okay, so when we refer to theta 0 in equations, just think of theta 0 as exactly theta 1. And as we mentioned here, theta TS and theta TB represent the respective number of shares of the risky asset and of the risk-free asset between times t minus 1 and t. So this means that theta T, S, and theta TB, they're known by time t minus 1. Okay, so at t minus 1, we know theta ST and theta BT. So this is what we call a trading strategy. So again, analogously to what we did in the one period case, we can define the portfolio value corresponding to some trading strategy. Okay, so for a trading strategy, theta, which is the dynamic allocation between the two assets in the portfolio, the portfolio value at time t for that trading strategy is theta ts st plus theta tb bt, which is the number of shares of the risk-free asset in the portfolio at time t times the price of the risky asset at time t plus the number of shares of the risk-free asset in the portfolio at time t times the number of shares of the risk-free asset at time t. Okay, so this is pretty much like the definition we had in the single period case, but here we must have that the number of shares in the portfolio depend on time, because we saw that for a trading strategy in the multi-period case, the composition of the portfolio or allocation to both assets changes through time. So here, to obtain the portfolio value at time t, we must specify at which time we look at the number of shares in the portfolio. So this defines the portfolio value, and now a very important definition, which is necessary for subsequent option pricing schemes, is the following. It's the notion of self-financing trading strategy. Okay, so before giving the mathematical definition, I'll give an intuitive definition. So portfolio is said to be self-financing if there are no cash injections or infusions, nor withdrawal of cash from the portfolio at any time step except at the initiation, or inception at time 0. So at time 0, you can put some money in the portfolio, but then at all subsequent time steps, there should be no infusion nor withdrawal of capital within the portfolio. So this is the definition of self-financing. And why is it called self-financing? It's because since we don't inject capital in the portfolio, every time some asset is purchased, this purchase is done by selling from another asset. So you sell from another asset, you obtain capital, and you use that capital to buy the new asset. So if you want to buy some asset in that portfolio at any time, you have to do it by selling of some other asset you have. Okay, so it's self-financing. You don't finance the portfolio throughout its life. You use its existing amount of funding within the portfolio to fund all subsequent purchases of assets. So how can we express that mathematically? A trading strategy theta is said to be self-financing if for all time steps t, uh, okay, theta t plus 1 s st plus theta t plus 1 b bt is equal to the same expression, except that the thetas are now indexed by time t instead of t plus 1. Okay, so this is just the equation, but now let's try to make sense out of this. Okay, so what's this value to the left? This is the, okay, so recall that theta t plus 1 is the portfolio composition between time t and between t and t plus 1. Conversely, theta t represents the composition of the portfolio between t minus 1 and time t. So here, this means that this quantity to the left is the portfolio value right after rebalancing at time t, okay? Because this composition is held from time t to t plus 1, so it's right after the rebalancing at time t. What do we mean by rebalancing? Rebalancing is just changing the number of shares within the portfolio, okay? Whereas to the right here, this is the value of the portfolio right before the rebalancing at time t, because theta t represents the number of shares in the portfolio between t minus 1 and t. So if we look at that, this means that a trading strategy is self-financing if the portfolio value right after rebalancing the portfolio at time t is the same than the portfolio value right before the rebalancing. And this means that having the same value before and after rebalancing means that during the rebalancing of the portfolio, as you changed the number of shares within the portfolio, you didn't inject new capital in the portfolio. So not injected new capital means that you didn't change its value, so the value of the portfolio must be the same just before and just after rebalancing. And this means that if you had to purchase some more of stocks in your rebalancement, it's because you sold some shares of the underlying asset to get the capital required to buy stocks, for instance. Okay, so this is the definition of a self-financing trading strategy. Okay, so again, in this multi-period model, we might be wondering what are the values for U, D, and R, which would make sense. And by making sense, I mean what are the values which would preclude the presence of arbitrage, or which would cause the presence of arbitrage opportunities. Okay, so it's possible to show that for the multi-period framework, there's no arbitrage opportunities if and only if U is greater than exponential of R, which is greater than D. Okay, so this is exactly the same condition than for the single period model. So the result is the same. We've proven it for the one-step case, but for the multi-step case, we won't provide the proof. And the reason is that in a more advanced course, which is MACF 401, we do provide the proofs for these results. So we don't want necessarily to duplicate material. So if you want to learn more about this, I encourage you to take the MACF 401 course. So In future slides, we're going to assume that u is greater than exponential of r and greater than d, because this entails that there are no arbitrage opportunities in the market, which contains only the two assets B and S. Okay, so now we're going to introduce a bit of notation which will be required subsequently for the examples we're going to go through. Okay, so we're going to consider the following notation. Vt theta k will define the time t value of the portfolio. So V stands for portfolio value, T time T, of trading strategy theta. Okay, theta here denotes the trading strategy. And here this K in parenthesis, this will denote conditionally on the time t underlying asset price being S0 UK dt minus K. And what we mean here, this means that when K upward movement occurred for the stock between time 0 and time t. Okay, so in a nutshell, let's repeat that. Vt theta k is the portfolio value at time t for the trading strategy theta, assuming that there were k upward movements in the stock within the portfolio. K movements on upward movements on the stock within the market. Same thing here, CTK denotes the time t price of some derivative we're going to introduce in the market, given there were k upward movements in the stock between time 0 and time t. Theta t plus 1 sk is the number of risky asset shares in the portfolio between time t and t plus 1, again conditional on k upward movements in the stock previously. Okay, so here this k denotes the number of upward stock movements until time t, and here recall that theta t plus 1, we said it had to be predictable, but predictable means that it had to be known by time t. So indeed, by time t, you know the number of upward movements in the stock by that time. So it makes sense to say that this guy is predictable if it depends on the number of previous movements, upward movements in the stock. Okay, so here the trading strategy we can consider can be random. Well, will be random in future examples, but by random it must depend exclusively on past information, what has happened before. So you cannot make the current investment decision in terms of number of stock shares in the portfolio based on what will happen in the future. Okay, so when you decide the allocation of the portfolio at time t, you decide theta t plus 1, and this can only depend on values of the stock until time t and not future values of the stock. So same thing, theta bt plus 1k is the number of risk-free asset in the portfolio between t and t plus 1, provided you had k upward movement in the stocks until time t. And finally, same thing, we're going to define STK being the stock price at time t if you had k upward movements previously, which is S0 UK, no, because of k upward movements, dt minus k, meaning that you had, since you had k upward movements, you must have had t minus k downward movements up until time t. Okay, so now for the remainder of this video, we will provide an example to show how options are priced in the multi-period framework. Okay, so we're going to start with an example, and hopefully by looking at that example, this will make the subsequent theory that we'll introduce in later videos more clear. Okay, so instead of giving the theory and providing an example, I think for this topic it's easier if we provide the example directly, and then the theory will be understood more naturally in that case. Okay, so this example, it's taken from the exercises list, so you can repeat that in exercises to make sure you understand the procedure. Okay, so we want to find the price of some European call option on the risky asset with strike k is equal to 100. Okay, so here what we're gonna do, we're gonna want to add a derivative to our market, and we try to figure out what would be the price of that derivative at time 0. So the derivative we're going to consider here is a European call option on the risky asset. So the underlying asset is the risky asset. And we want to figure out what should be the price for that European call option at time 0. And we're going to assume that here K is 100. So you have the strike being 100. U and D are respectively 1.12 and 0.93. The risk-free rate is 2%. The initial stock price is 100. The probability of going up or down in the tree is respectively 0.6, and we're going to assume no dividends. Okay, so here I'm going to sell the punch here. That P here won't be needed to find the solution. Okay, so why is that the case? Well, let's go back to the previous video. We mentioned that the price of a derivative was the expected discounted payoff of the portfolio under the risk neutral measure, not under the physical measure. Okay, but if you go back to the formulas, maybe let's go back a few slides here. One thing we didn't talk about but is very important is that the probabilities associated with the Q measure, the risk neutral measure, they don't depend on P. So here, in the one period case, the price of the derivative here, which is this expression here, doesn't depend on P at all. Okay, this is counterintuitive, but this is the case. Okay, so you might think that if the stock has a higher chance of going up, then a call option would be worth more. But under this framework, it is not the case. Okay, so P is not a pricing input for your option, although it's counterintuitive. And the same thing will happen in the multi-period framework. We're going to see that shortly. So let's go back to our example. So here, this is the parameters for our problem. And I realize I just forgot to put one here, which is the maturity of the option. So we're going to consider, I think it's, okay, we're going to use a 2-period example. Okay, so capital T should be equal to 2. So we have 2 time periods here, and the option expires at the end of the second period. So this I forgot to put it here, but you should add capital T is equal to 2 here. Okay, so let's try to find a way to price options under this example. And the idea we're going to use is the same than what we used previously. We're going to use the idea of replicating portfolios. So we're going to try to find a portfolio that has a final value exactly equal to the payoff of the derivative. Furthermore, we'll make that portfolio self-financing. So we are going to assume that this portfolio is set up at time 0, and then we don't need to inject capital in that portfolio. And then just by rebalancing itself, the portfolio will have a final value exactly equal to the derivative payoff. And from that, we will be able to conclude from the law of one price that the initial value of the portfolio should be equal to the price of the derivative. Okay, so this is a a lot was said here, but let's go through the example to make the thing more clear. Okay, so again, we want to construct a self-financing portfolio and find the trading strategy which will give us that the probability that the terminal value of the portfolio is equal to the payoff of the derivative we're trying to price is 1. Okay, so we want to find a self-financing trading strategy which is replicating, and by replicating we mean that the terminal value of the portfolio is equal to the payoff of the derivative with probability 1. And as we just said, through the law of one price, this will imply that the option price at time 0 should be equal to the price of the replicating portfolio at time 0. Okay, because both the portfolio and the option, they give the same payoff at time t. Moreover, at previous time steps other than t, there's no cash flow involved because the portfolio is self-financing. So at time 0, the price of both financial instruments, the derivative or the portfolio, should be the same because for all subsequent time steps, cash flows are identical. Okay, so this is the law of one price applying. Price of the option should be equal to the value of the replicating portfolio. This is a very important lesson from the course here. Okay, so the first step to solve this problem is to find the value of the underlying asset at each node of the tree. Okay, so we said that the underlying asset starts at $100, and at each step there are two possibilities. Either it goes up and we multiply its value by 1.12, or it goes down and we multiply its value by 0.93. Okay, so from 100 it goes either to 112 or to $93. And then at the next step, let's say it's at 112, it can be either multiplied by 1.12, which gives this value 125.44, or if it goes down, it's multiplied by 0.93, which gives the value 104.16, or if it's at 93 and it goes down, it's multiplied by 0.93 again, which gives 86.49. Okay, so this gives us the possible value of the underlying asset at all nodes of the tree. So once we know the value of the underlying asset at all nodes of the tree, we can look at the terminal nodes and determine what would be the payoff of the option at all these nodes. Okay, and why do we need the payoff? Well, it's because we want to find a replicating portfolio, so we will want to find a portfolio whose final value is equal to the payoff. So if we want to know the final value of our portfolio, we must know what the payoff of the option is. Okay, so as we mentioned, we want to know what would be the final value of the portfolio at each node at time 2 of the tree. And to get these numbers, we will need to find this here. Okay, and what we will see, or what we've discussed up to now, is that because the portfolio will be replicating, so because the value of the portfolio at the last time step will be exactly the same than the price of the option, then at all prior time steps, both the portfolio price and the price of the derivative should match. Okay, so these two trees, this tree represents the value of the portfolio at each step. This tree represents the price of the derivative at each step. Both trees should have identical values. Okay, so here recall a bit the notation. So for example, V00 means the time value, the time 0 value of the portfolio if you had zero previous upward movement in the stock. So for example, if we try to interpret this quantity, this is the time 2 portfolio value if you had exactly one prior movement in the stock. So either you went like this or like this. Here you had a single upward movement, so you end up here. Okay, same thing here. For example, C10, this means the price of the derivative at time 1 if you had zero upward movement in the stock. Okay, so now the next step will be to find these guys. So we found the underlying asset value at each node of the tree. So this allows us to calculate what are the payoffs for each possible terminal nodes of the tree. Okay, so this slide I won't repeat it. It's just recalling what I just said in the previous slide. It's because the portfolio value is equal to the derivative payoff with probability 1 at the last step. Then through the law of one price, the derivative price should be equal to the portfolio value at each time step and under each scenario. And by scenario, I mean the number of upward movements in the stock price. Okay, so as we said, now that we have the values of S2, the underlying asset value for each node of the tree at time 2, we can find the payoff of the option in each scenario. So here the payoff of a call option would be the maximum between 0 and S2 minus K. So you can replace S2 by its value in all scenarios. So here, if you have two upward movements, S2 would be S0 U2, which is 125.44. K, recall it was 100. So in that case, the payoff of the option would be 25.44. So here, in the second scenario, if you have an upward movement followed by a downward movement, or a downward movement followed by an upward movement, the stock price at time 2 would be S0UD, because one upward movement, one downward movement. So we saw that this was $104.16. So if you subtract $100 for the strike price, this is 4.16. And here, if you go here, the terminal value of the stock was what was the value? Was $86. So here the maximum between 0 and 86 minus 14. So this guy here would be negative. So the maximum would be 0. So on that node here, you just wouldn't exercise the option and its value would end up being worthless at its value would be 0. So no payoff. Okay, so it's good. So now we have the payoff of the option at the last time step. This gives us the terminal portfolio value for each the nodes. So our portfolio should replicate these values at the last time step. Okay, so this is good. By the laws of one price, as we said, at the last time step, the value of the replicating portfolio should be equal to the derivative price. But now what we want to find here is what would be the value and composition of the replicating portfolio at each of the earlier stages. Okay, so how can we manage to set up a portfolio which will have exactly these values in all the possible scenarios we've contemplated? Okay, so this is what we're going to figure out next. So we're going to focus on one branch of the tree. Okay, so here we know that if we're at that time point here, so if we're at time 1 and assuming that there was a single upward movement of the stock previously, then we want to set up a portfolio at this point, so at time 1, which has the following value, which has a value of 25.44 if there's an upward movement in the stock, or which has a value of 4.16 if there's a downward movement in the stock. So these values should be the final portfolio value if you want to have a replicating portfolio. Okay, so in this case, we can do some calculation which were analogous to what we did for the single period binomial tree. Okay, so let's see that. So you should set up a portfolio at time 1. Okay, so what do we mean by setting up a portfolio? It's identify its composition, which is the number of stock shares between 1 and 2, so theta 2s, and the number of risk-free asset shares between time 1 and 2, so theta 2b. And here the parenthesis 1 says that it's assuming we had a single upward movement in the stock previously. So we want to find these two unknown quantities, which is the portfolio composition at time 1. And we want to find them such that the value of the portfolio would be equal to V22 if the underlying asset price goes up, because if the underlying asset price goes up, there will be exactly two movements of the underlying asset in total. Furthermore, if the underlying asset price goes down, then you want the terminal portfolio value to be V21, which is the portfolio value if there were exactly one downward movement up to time 2. Okay, furthermore, by definition of V2, we have that V2 is given by this. So it's the number of shares of the stock between time 1 and time 2 times S2, the price of the stock at time 2, plus theta 2b times B2, the number of risk-free asset shares at between time 1 and time 2 times the time 2 price of the risk-free asset. So if we combine this equation here and these two equations here and here, we obtain the following. Okay, so here, first equation, if we take this equation here, this is V22, must be equal to the portfolio asset, portfolio value at time 2. And here, if there were exactly two upward movements of the stock, then S2 here would be replaced by S0 U2. This is the value of the stock if there were two upward movements of the stock. Okay, so portfolio value should be equal to number of stock shares in the portfolio times the stock value at time 2 if there were two upward movements, plus number of risk-free asset shares times the price of the risk-free asset at time 2. And you should do this, so this is for the first equation, this is for the second equation. You should do the same, assuming a downward movement occurs next. So if there's a downward movement occurring from time 1 to time 2, then the terminal portfolio value should be equal to this. So this is what our target, what the portfolio value should be to have replication. And this is by definition the value of the time 2 portfolio. Assuming, so here this one means that there was exactly one upward movement of the stock between time 0 and time 2. So the stock value at time 2 is equal to S0 UD. So here we have a system of two equations with how many unknowns? The only unknowns in this system of equation is theta 2b and theta 2s1. Okay, so theta 2s1 is one unknown. This is another unknown, theta 2b1. So we can solve the system of two equations to unknown and put it in okay, you can put it into a matrix and solve the matrix equation, or you can solve it manually as you've did, like using regular algebra, as you've learned in high school. And then the solution to this would be the following. So it's possible to show that theta 2s1, the number of stock shares in your portfolio, would be equal to the following quantity, which depends on what should be the terminal portfolio values to achieve perfect replication of the payoff, and of other quantities such as S0, U, and D. Same thing, you can isolate the value for the number of risk-free asset shares in your portfolio, And if you just plug in the values you've obtained here, the number of stock shares at that node should be 1, and the number of risk-free asset shares at that node here should be minus 86, $96. Sorry. Okay. So if we go back here, we've identified theta S and theta B at this node here, such that if there's an upward movement in the market, the portfolio value will be such that you achieve replication. So it's the portfolio value will be equal to $25. If the stock price goes down, our portfolio, which we've identified, will have a value at 4.16. So in that case, the portfolio we've identified replicates the payoff derivative in both scenarios. But now what remains to be calculated is the value at time one of the portfolio. And why do we want to calculate that information? It's because the time one value of the portfolio will be the price of the derivative at time one. So let's make this calculation. We've calculated the number of stock shares in the portfolio at the node we were interested, the number of risk-free asset in the portfolio for that node also. So as we mentioned, we'd like to have the price at the same node of the derivative, and the price of the derivative would be the price or the value of the replicating portfolio at that node. And what is the value of the replicating portfolio? We can use the definition of portfolio value. So portfolio value is the number of stock shares in the portfolio times the price of the stock share plus the number of risk-free asset shares in the portfolio times the risk-free asset. So we can just substitute theta here, theta S2 and theta B for the values we've calculated at the earliest slide, and we can replace S1 by S0U because at the node we were at, so if we go back here at this node, there was exactly one single movement of the underlying asset, so one single upward movement of the underlying asset. So S1 at this node here is exactly equal to S0U. So we can substitute, if we go back here, we can substitute S1 by S0U. So this gives the following. The price of the replicating portfolio we've just calculated earlier is equal to 1. So we had 1 share of stocks in the portfolio times the stock price at this node was 112. And here, plus the number of risk-free asset shares in the portfolio, which was minus 86.08, times the value of the risk-free asset at that node, which was 1.02. Okay, so it's not exactly 1.02 because it's the exponential of 0.02. So this gives a value of 13.98 to both the replicating portfolio and then through the law of one price to the derivative at that node. Okay, so we know that at this node here, the price of the option must be 13.98. And the reason for that is because the derivative is worth this amount because the derivative price must be equal to the replicating portfolio, and the replicating portfolio at this point has a value of $13.98. $98, sorry. Okay, so we've identified the price of the option at this node here. So now the next step would be to identify the price of the option at that node. And to do that, we can do exactly the same things we've done earlier. Same system of equations, so we can focus on that branch of the tree and run similar calculations. And then we won't repeat the calculations because they're conceptually identical to what we did. We can show that the value of the option at this node should be 1.93836. Okay, so now we know the value of the option, and similarly of the replicating portfolio at each of the nodes except for the initial node. So how are we going to calculate the value of this node here? Well, we're going to use again the same technique. So if we can set up a portfolio at time 0 such that the portfolio value becomes 13.98 if there's an upward stock movement, or the portfolio value becomes 1.936 if there's a downward stock movement, then this portfolio will be replicating. Because we've seen earlier, we've proved that if the portfolio value has a value of 13 here, then this portfolio can replicate the payoff of the derivative in both scenarios. If you obtain a portfolio value of 1.936 at this point, then you're able to replicate the payoff of the derivative in both these scenarios here. Okay, so the only thing that's left is to set up a portfolio here, which will have either this value in the upward if there's an upward stock movement, or this value if there's a downward stock movement. And this, again, it would be analogous to a single period binomial tree calculation for a derivative which would have this payoff here and this payoff here. Okay, so the calculation would again work like a single period binomial model. Okay, so as we mentioned, we want the option price at time 0, which is C00, and through the law of one price, the price of the option at time 0 will be equal to the price of the derivative at time 0. Okay, so what equations are we going to use? Well, we know, if we go back one slide, we know that we must have a value of the portfolio at time 1 of either 13 after an upward movement or 1.9 after a downward movement. Okay, so here we can use the formula for the value of the portfolio at time 1. So the value of the portfolio at time 1 is the number of shares of the give me 1 second. Yeah, okay. Okay, no, so sorry. This is a calculation we've done earlier. Okay, so this allowed us to find 13.98, which is the value of the replicating portfolio at the first node. Okay, so here, this is what we want to do next. So here, what we wanted to do at the initial point was to calculate the number of shares in the stock and the number of shares of the risk-free asset in the portfolio to obtain a value of the portfolio being V11 if the underlying goes up. So this value was 13.98, or V10, which was 1.9 if the underlying asset price goes down. So here, what's going to happen, we can use the formula for V1 theta. So here V1 theta, we can recall it's equal to theta 1s times s1 plus theta 1b times b1. And in that case, coupling these two equations, so these ensure that our portfolio is replicating. And here, this is simply the definition of the portfolio value at time 1. So if we couple these equations with that, where we can replace S1 by S0U in the case we have an upward movement in the stock, or S0D in the case where we have a downward movement of the stock, then we have again this system of equation where we have two equations, and the two unknowns are the composition of the replicating portfolio at time 0, so number of stock shares, number of risk-free asset shares at time 0. So you can again solve this system of equation, and if you do that, you can isolate the value of theta 1 S0 and theta 1 B0, which are respectively the number of shares of the risky and risk-free asset at time 0. So 1 means between time 0 and time 1, so this is decided at time 0. And this 0 in parenthesis means exactly 0 upward movements of the stock previously. So you can isolate these values in the previous system of equations. So this gives you that tells you that you should hold 0.63 shares of the risky asset and minus 55.89 shares of the risk-free asset if you want to obtain a replicating portfolio. So doing that, well, this gives us the composition of the portfolio at the initial node. So if you know its composition, then it's straightforward to know the portfolio value. So the portfolio value will be equal to the number of stock shares times the initial stock price plus the number of risk-free asset shares times the initial risk-free asset price, which is equal to 1. So we can simply replace these two guys by the values we've calculated in the previous slide. So if we do that, replace S0 by 100, B0 by 1, this gives us that the initial replicating portfolio value is 7.502. And by the law of one price, because it's the initial portfolio value, it must also be the initial value of the option. Okay, so this concludes the calculation of the European option. Okay, so here there were a lot of calculations involved. I expect you not only to listen at the thing once, at the video once, without stopping it. I expect you every time there's a calculation, please stop the video and make sure you understand that step thoroughly. Okay, so there's a lot of calculations that were done quickly in this lecture, but please take the time to ensure that every single step shown here is clear to you. Otherwise, you'll miss the key points to understand how the pricing is done. Okay, so we'll stop here, and then in the next videos, what's going to happen is we've presented an example here, but now we'll formalize everything we've done here into formal theoretical results, which can give you formulas to price any options or any derivatives in that multi-period binomial market. So thank you, have a nice day, and we'll pursue this chapter shortly.